Okay, so today is arguably another one of the most useful and exciting lectures. Useful in a way that even if you don't end up doing operating systems or anything like that, understanding how synchronization in multi-core machines works is very useful, like for multiple different reasons. So again, up until now, everything what we were discussing was happening on one single machine or on one single core, right? We booted, created the world, started running shell. We know how file systems work, system calls, page tables, everything, right? But the reality is that anything what we run today, or almost anything, besides some fraction of embedded systems, runs on multiple cores, right? The question is, how does it work? How does it get initialized and stuff like that? So that's the topic of today's and Thursday. So the thing is the following. So I was saying that x86 will bootstrap other CPUs, right? So let's take a look at how it's done. Again, back to our wonderful main function, which we kind of like, we all know by heart now, but typically we said, okay, we end up here, MP main enters the scheduler, and that's what we were talking about. Scheduler does context switches and stuff like that. But before entering the scheduler on this very first CPU core, which we were discussing up until now, x86 invokes this function, start others. And this function wakes up other CPUs. Does anyone remember what these other CPUs are doing at this point? It's part of the boot lecture. We talked about it briefly. Do you remember those terms, application processors and bootstrap processor? Anyone? Not. So remember that the system, remember the stages of boot when caches were not even initialized and stuff like that. So essentially, those all the CPUs in the system, they ran for a little bit at this point. They actually initialized caches like microcode stuff, right? Stuff like that. But one of them was chosen as a bootstrap CPU. And that's the CPU we were running on. And all other CPU are sitting, they're called application processors. They're sitting in some kind of a waiting state. Despite the fact that they ran for a little bit, BIOS left them in this, in a state in which nothing is running. And all of them are kind of waiting for a special magical interrupt. And so this function, start others, will eventually send those interrupts to all of these CPUs, and these CPUs will start running something. And not surprisingly, all of them will start running scheduler, right? So because we want to schedule processes on all CPUs, right? So start others is the function which does it. Again, so what we're doing here, the CPUs is sitting there, this application CPUs, they're sitting there waiting, and they will start running in real mode. So we have to really switch them from real mode, enable segmentation, meaning switch them to protected mode, then enable paging and start booting into something main-like, right? And so what happens here is that as part of this magical interrupt, you can provide a start address, meaning that asking the CPU to set the instruction pointer to a specific address. However, the idea is that we need some kind of a boot sequence to run at this address. And again, everything is real mode, so it should be at the lower part of the address space, like physical memory still. Those CPUs simply can access physical memory. Very similar to how we were booting BIOS put us at 7C00. So the operating system just picks one address which it believes is available, and in this case it's 7000. Copies there and init sequence, and essentially will send this magical interrupt waking up other CPUs. Essentially how it works is the following. So this function start others, it says, okay, sure, we will initialize a variable. Since this CPU we are currently running on runs in virtual mode, so we cannot really access physical addresses directly, right? So what we do here, we translate this physical address 7000 with this P2V macro. What address do we get from this? Do we know? Do we remember how P2V works? Right, exactly. So it's like we know that we mapped all the physical memory with a shift of 2 GBs. So it's 2 GBs plus 700. Okay, so and what we're doing here, we play the same trick. We play this linker trick similar to how we use the init sequence. So we have a binary sequence which represents this bootstrap code. We will take a look at it in a second, and we like copy it at this address, right? And what we will be doing next is that for each CPU in a system, we will allocate a new stack. And essentially, so we have a loop. We say, look, we will support some number of CPUs. For each of the CPUs, since we already have memory allocation on this CPU, we allocate a new stack. Let's quickly do a poll just to wake up and warm up. The question is, what do you think will be running on this stack? So it's a little bit of a guessing game, but I'm pretty sure you can guess correctly. Let me enable it. Okay, activated. So again, the question, what will be running on this stack? Why do we need a stack? Well, still people are answering. Let me wait for a second. So let me maybe present and share, or not present, but just share this thing. So this is the, sorry, just quit this thing. These are the answers which I have right now. So someone who like said init process on the new CPU, can they justify their answer? Or anyone like, let's, can anyone defend any of these answers with some meaningful logic?
I can argue why it's not an init process.
Okay, sure, go for it.
Well, the init process is automatically starting a shell. If you have multiple CPUs running in it, then you have a bunch of shells running. You don't want them. You just want them.
I agree with this. So does everyone agree? So your classmate is saying that, yeah, we really need just one shell, which means we need probably one init, right? Init starts shell, shell welcomes us into the system, we interact with the shell. On a real like Unix machine, obviously, it may support multiple shells. You can connect remotely or have multiple whatever terminals and everything will be running. But on x86, we need just one init, one shell. I agree with this. Okay, so definitely not the first choice. And definitely not the second choice because we don't need the two shells, right? What about the scheduler? Scheduler on the new CPU. That's a good choice, right? So people are nodding. Any questions? Yeah. I agree with that. So that's the main logic. So like, that's why we're bootstrapping the CPUs. And in a way, each CPU in the system will be responsible for picking some available process from a pool of runnable processes and scheduling and running it, right? And remember, the way x86 structures the context switch sequence, it needs this stack for the scheduler. You can argue, okay, well, by the way, we can rewrite x86 in such a manner that it's not necessary and just switch from one process to another. That's also possible. But x86 does leave a scheduler running on each CPU. And so correct answer is yes. So you need to run this scheduler. And this is the stack for the scheduler. And obviously, like, we're just guessing. So in a second, I will tell you for real how it works, but that's the correct answer, right? And then each next process on any of the CPUs, every time we create a new process, you just seen it in this last homework, we'll be using a sequence which allocates a new kernel stack. for each process, irrespectively of the CPU. And in fact, the processes will be not in any way tied to a specific CPUs. They will be constantly bounced between them. We'll see in a second how it works. So, right, but essentially it can start running on one CPU, context switch, be in a runnable queue, and then scheduler on another CPU picks it up and runs on a different CPU. So it's also important to understand this. Okay, let me close the poll for now and go back to the lecture. Just a sec. This one. This one. Do something else. Here. Trying to figure out my Zoom here real quick. Up. Here. Okay, so hopefully it's sharing the right screen at this point. It's not guaranteed. Now I'm looking for my PowerPoint slide deck. Finally, I found it. Okay, cool. So what we're doing here is that for each of these CPUs, we allocate a new stack, right? So we got this point. And what we think is that, by the way, so we will pass some additional arguments. For each CPU, those arguments will be slightly different. So essentially what we will be passing is we pass three things. We pass the location of the stack itself, the address of the entry function. So this is what the CPU will be using to set this instruction pointer to. And we're using the entry function of this MP-enter. And we also passing the location of the entry page directory. So we are once again, we are using entry page directories, this very simple page directory, which uses 4 megabyte pages and just has two entries, the one which maps the first 4 megabytes one-to-one, and the one which maps 2 gigabytes plus 4 megabytes of virtual memory to the first 4 megabytes of physical memory, right? So exactly how we were doing it during the boot, because each CPU will kind of like go through the same initialization sequence. And at this point, we say, look, we got it. So the entry code sits at 7000. We passing this as an argument to this function, which sends this magical interrupt. And this magical interrupt just goes and wakes up the other CPU. So essentially, we do it by one, so in a loop, right? In the end, this is the function, send an interrupt, and a CPU is woken up at specifically this location. So this will be mapped at X700 in physical memory. And this is implemented in a file entry other. It's a sequence which is similar to a boot sequence of which we've seen before. It's slightly simpler. So what we are doing here, we again disabling interrupts just in case, zero out all the segment registers here, just to make sure that if BIOS left any of those in a non-zero state, we need to make sure that nothing will happen and we know what's going on. We load the global descriptor table, again, the very same global descriptor table which we're using. Enable 32-bit mode of execution, so essentially saying, okay, please use it, set the flag, do long jump to start 32, and up here, this is very similar to your homework 3. So again, here we're initializing the segments with a kernel data and a kernel code. So kernel code was initialized here. Kernel data is here, so we load them in all these segments. Continue booting. After that, we said, okay, we are ready to enable paging. So we set the 4 megabyte page extensions, load the location of the entry page directory in the control register 3, so root of the page table, turn on paging by, again, modifying the flag, CR0. And at this point, we're ready to jump back to C because we don't need to do anything else. So we said, okay, our stack will be loaded in the ESP, and essentially we're gonna jump here to this MP-enter function. And these 3 locations, this one, and this one, were passed as essentially just if this was the start of the code, we're passing it right below it as 3 arguments. So it's a little bit of a hackery here, but just it's a convention. You can pass those things anywhere. So essentially anywhere in memory, you can put them, but like x86 says, okay, start -4, start -8, and start -12, right? So, but at this point, we jump into np-enter. np-enter, okay, sorry, I have to like walk through those slides. np-enter says, okay, sure, we get it. So we will switch to a real page table. So notice that since we already initialized memory management and everything, so we don't need to do it twice or multiple times on all of these CPUs. We simply say, okay, we already have a page memory allocator, so this will allow us to construct a real page table. Again, this page table will be running and will be used by the scheduler. After that, we initialize like interrupts, because obviously each CPU has a physical interrupt descriptor table register, so it has to point to the interrupt descriptor table. Initialize here, like let's just walk through it. So the way it works is that remember that on x86, each physical CPU is represented by this structure, struct CPU, and there is a function, the CPU ID. And if you invoke it on a specific CPU, it will return the CPU ID. So on the first bootstrap CPU, it returns 0, then it returns 1, then it returns 2, right? And so x86 maintains an array of physical CPUs. And essentially what it does is just, okay, says index into this array, gets the instance of the CPU data structure, and essentially each CPU will have its own global descriptor table at this point. Again, it's the same global descriptor table which maps the kernel code and data segments with from 0 to max address with privilege for privilege level 0, and the user code and data is mapped with privilege level 3, right? And then this global descriptor table is loaded in on this specific physical CPU. So let me ask a question, kind of a tricky question, which I might ask on the exam. So why do we need a separate instance of a global descriptor table on each of the CPUs? That's kind of a tough question, but worth understanding. It's because of the TSS, but can you give us more details? That's correct.
So
Mm-hmm.
So yes.
More or less correct, but let me just reiterate what you said one more time. So imagine that, just for the sake of example, that system has just 2 physical CPUs, right? And on each of these physical CPUs, like obviously each of them will have its own instruction pointer, will have its own like global descriptor table register pointer, GDTR, right? And at some point, like obviously this instruction pointer will be pointing to some location and some main function of some process. Maybe this one is shell for simplicity, and maybe, I mean, whatever, maybe this one is init. This is realistic because we're already like running shell and init, right, on all the CPUs, not on all the CPUs, on the moment we boot into the system. So these are the 2 processes which are instantly created, right? And it can happen that the system will be running this shell on, like, it switch to the shell on one CPU, switch to init. If I ask you a question like, what is init doing? It's just like running in this infinite loop, checking, or whatever it was doing. It was waiting for the shell. But at this point, like these CPUs are physically autonomous, right? So everything happens really in parallel. And obviously, like both of those CPUs can have a timer interrupt because they have the logic of like counting time. And at some point, the timer interrupt gets triggered, like it gets delivered through the interrupt descriptor table. Interrupt descriptor table. What? ADT. And when we transition from the from privilege level 3 to privilege level 0, remember what the hardware is doing. The hardware has to figure out the kernel stack of this process, right? Because it actually saves these 5 things on the kernel stack, and then we jump to the vector 32, all traps, and save other registers on this kernel stack. And specifically, the location of this kernel stack is pointed by the global descriptor table. So if you have a global descriptor table, it will point, like more specifically, it will point to TSS, location of a TSS, and inside the TSS, there will be a pointer to this kernel stack, right? And of course, since this physically happens in parallel, this process also will need its own kernel stack. And obviously, since the hardware has to choose the different kernel stack on this other CPU, this different global descriptor table, GDT, will have a pointer to a different TSS, and inside this TSS, there will be a pointer to a kernel stack, right? So if we choose to have these 2 guys as a single instance, there's still a way to probably share them somehow by choosing different entries in the global descriptor table, but x86 essentially chooses to use different global descriptor tables, so they have a pointers to different TSS, and different TSS will have pointers to different kernel stacks. The main idea here is to have a private kernel stack per process and per CPU at any given point of time, right? That's why essentially every time we switch, between processes, we just reload this field in the global descriptor table to point to a process private TSS, because a process private TSS will have a pointer to a process private kernel stack. Make sense? Okay, so that's why essentially we initialize a private global descriptor table, although we don't do anything with the TSS. When we will be switching between processes, we will add additional entry in this CGDT, seg TSS, right? And this seg TSS will be pointing to a process private TSS, and a process private TSS will point to the kernel stack of the specific process we're trying to run. Okay, that makes sense. Sure. So in general, if we talk about this idea, so those variables which are kept in the CPU data structure are called per CPU variables, right? So there are different ways to implement those per CPU variables, but in x86, it's simply an array which you index with the CPU ID, right? Meaning that each CPU will have a collection of private fields. And just to make sure that we understand what these are, there are not many of them in x86, so it's just like we talked about global descriptor table, like tiny location in memory, which will be used for the TSS on this CPU, currently running process. Today, we're going to talk about disabling interrupts, and this is the counter which we maintain, how many times we do that recursively. This flag tells us whether the interrupts were enabled before we did the first push CLI, stuff like that, right? So, and a pointer to the scheduler context, we talked about it, and ID of the local epoch. I don't remember how this one is used. But anyway, so at this point, we are inside the MP enter, and MP enter ends by calling this MP main function. MP main function prints this string on the shell saying, okay, I have started a new CPU, loaded the interrupt descriptor table, enabled the interrupts, and essentially ends up entering the scheduling loop. And inside the scheduler, this guy on each CPU will be looking at the array of available processes. We'll scan through this array, pick one which is runnable, and we'll try to switch to this process, essentially just do a switch function here. And essentially this will be happening on each CPU in the system, right? So each CPU in the system will be running this scheduler. So it kind of explains what's going on. Let me stop here for questions. Any questions about how it works? And that's okay. So like those low-level details, kind of we bootstrap the CPUs, we understand it. But the real thing which we kind of want to understand how they work is really this. If I ask you a question, right? So how do different CPUs access one single memory, right? So we have multiple CPUs. I will just make sure we use 2 as an example. And there is one physical memory. And of course, okay, there is like some kind of a page table in between. So there will be like virtualization of this memory. So this is one virtual address space, another virtual address space, maybe a slightly different used on this CPU, right? So maybe like you have a move instruction, and this move instruction tries to read a location from memory. You, of course, do the virtual, this is a virtual memory to physical translation. It gets to some physical address here. My question is the following. What happens if maybe a different CPU tries either load or store EAX? Sorry, like slightly bad drawing, but the point is this. What happens if these 2 CPUs try to read and write the same memory location? How does it work? What do they see? Imagine this one is, one of them may be writing 1 into this memory location, and another tries to read whatever, and maybe the old location here was 0. Who can explain how it works? I mean, we all see it every day, right? So every time we program Python, something like that happens underneath. How is it implemented? Anyone knows? Do you guys know cache coherence? So how does cache coherence work? Who cares? Right? It's like this Saturday Night Live. Nobody knows. Right? Sure. Okay, let me explain. So this is the point, right? So this is why we need to understand it. And it's part of this class, but really it's part of any kind of programming language discipline or whatever you will be doing in modern machines. So let me make a small detour into this Intel memory hierarchy. So AMD and ARM have similar memory hierarchies. So it's like, we'll just use Intel as an example, just because I know it a little better. Again, so we know that I keep talking about the cores. That's not a big surprise. We all know what the cores are. The idea is that it has this collection of registers, obviously. Modern machines have private per core L1 data and L1 instruction caches. By the way, those are different. They are separated just for architectural reasons. And then a shared L2 cache, right? And when we say, look, we have multiple cores on a single CPU, it's kind of the same hierarchy replicated multiple times physically, right? So, and when you go, like, you buy a let me go jump ahead a little bit. When you go to a store and you buy a physical piece of hardware, Intel calls it a processor, right? So a processor can have multiple cores. And typical organization of modern CPUs, that certain things are sharing the same die as the core. So specifically here in my example, the core has a shared L3. It's not entirely true today because this shared L3 is not really like a single monolithic entity, but a collection of L3 banks which are connected by a very fast communication protocol. But essentially, we can think of those as a shared cache, right? So because each core will have a private L1, L2 caches, right? And a shared L3 cache. And also there will be a memory controller, PCI bus controller, and QPI link, or it's the link which will implement a cross-core communication. So let me just explain how it works. So a memory controller really connects you to the DRAM banks, which you like plug on the motherboard, right? So it's a piece of logic when you essentially have a cache miss. When you have a cache miss, the last level cache says, okay, I don't have a cache line. I will explain it in a second. The memory controller sends the request to the DRAM banks. In practice, on Intel, again, it's not a single memory controller, but it's like 2 or 3 these days, just again for performance reasons, but you can think of it as a single one. Similar, like this PCI controller, essentially, the magic here is that, remember, there is certain regions of memory which in practice don't go to the memory controller, but they go to the devices, right? So like kind of like a frame buffer where you were printing the hello world, right? So this magical bias mapped regions implement memory mapped IO, and this essentially the logic of this PCIe controller sends those requests to external peripheral interfaces. Like in this example, it's a PCIe attached disk, right? And finally, this QPI controller, QPI stands for Quick Pass Interconnect, and this day Intel calls it, instead of QPI, they call it UPI, Universal, I think, Pass Interconnect, but essentially it's a cross-socket link. It allows this machine to send messages to other processors in a system, right? And essentially, when you buy a laptop or a phone, it will have just one processor, right? So essentially, that's enough for like desktop and mobile use. When you go in a data center, majority of the machines will have two or more processors. It's not always more than two. Two is a kind of a typical kind of sweet spot, because if you buy more of them, this cross-core communication, this link will take too much time. But one important observation, which I keep bringing up in this class, is that if you take a look here, you will notice that the memory is attached at least at two places here. And it's truly the case. So there is not like a single, like you can configure machines to have all the DRAM banks on one of these connections, but then this core will have to communicate to this memory, which will take longer, as opposed to like going to its local memory, which is like way closer. And we'll discuss the numbers in a second. And also what's important here is that the PCI devices are also attached to individual like PCI controllers. So there will be a notion of a local device, meaning that it's a little bit closer to you, it's a little bit faster, and a remote device. And so again, when you go and build like data center scale systems, so this proximity of those memories and devices kind of becomes important, right? Any questions about this? We understand this picture? Okay. So now let's imagine we do a cache load. Just essentially have a move instruction, essentially something what like loads an address, like a load instruction. On this core, we execute a load, right? It will obviously go to L1 data cache, because I mean registers are local to the pipeline, but essentially if we're loading an address, the very first thing which the CPU is doing, it says, okay, I will try to locate this cache line in L1 cache. Do we understand what cache lines are? Like why? Essentially all communication. So even if you're trying to read a byte, like essentially you do a byte load, so you're trying to load 8 bits. In practice, all the communication between these layers of this hierarchy plus the memory will be in the units of the cache lines. Does anyone remember the size of the cache line on Intel? It's similar to other CPUs as well. 64 bytes, correct. So it's 64 bytes. And so essentially, even if we try to read 8 bytes or 1 byte, the whole 64 bytes will be like moved around. Okay, fine. So L1 cache plays this cache coherence protocol, and it just in general says, okay, maybe I don't have a cache line. And by the way, I wanted to like, here the font is a little small. So a read from a register, I can say, let's just go over these numbers one more time. A read from a register takes you 0 cycles, because it can be done within the same, roughly speaking, within the same cycle of a CPU, right? So essentially the logic of a pipeline allows you to read the registers. I mean, the pipelines are deep these days, but roughly speaking, you waste no time. Although, okay, it can be debatable, but like forget about it for a second, right? But how, like, again, just make sure that we understand those numbers. How much it will take you, how long it will take you to read the data from L1 cache? I keep asking this question, so by now, probably you guys should know. A load instruction, which touches the L1 cache, how long does it take? A little less, so than 5. Anyone else? Better number. Okay, I ask differently. Do we remember which resource to use to verify this number? If suddenly if you care about it, like tomorrow suddenly. Almost. Intel doesn't really publish those numbers, but another person, a professor from Europe, Agner Fogg, like who benchmarks all the existing CPUs, so just goes and like tells you these numbers, right? But okay, they're available online, but roughly speaking, it's 2 to 3 cycles. So, but again, like remember the name Agner Fogg, just to make sure that we understand that if anything, we can go and essentially read those numbers. Where is it? Where's my anything? I actually I'll come back to numbers in a second. What I wanted to illustrate here is that idea that if the cache line, let me like enroll here. If the cache line is not found in L1 cache, L1 cache talks to L2 cache saying, okay, do you maybe have the cache line? L2 cache says, okay, in this example, no, we don't really have the cache line. It talks back, it talks down to to L3 cache. L3 cache says, okay, I don't really know where this cache line is. At this point, it issues a read to memory controller. Memory controller goes to memory banks, like gets the cache line. In my diagram, it's this bool line. Bool line is typically like brought to all the caches, although it's no longer true again on Intel or in other CPUs. So it may happen that the cache line really just brought to L1 cache and not L2 and L3, but just for simplicity, let's assume this inclusive cache. So cache line actually is left in all the caches of the caching hierarchy. So what I wanted to explain here is, okay, we loaded the cache line on one CPU, right? Back to my original question. So imagine we have a different CPU, which tries to do the load, Hey guys over there, you either leave the class or you keep quiet. Is it okay? Like there will be no quizzes today. It's fine, you can go home. So we do the load, like load talks to the local L1 cache, talks to the local L2 cache, L2 cache to the shared L3. L3 says, okay, I actually have this cache line because it was just loaded. So an L3 replies with this cache line, and I guess essentially just gets inserted into L1, L2 of this core, right? So everything happens in terms of like cache lines. So next question, what happens if one of these cores tries to write into this cache line? What do you think will happen? Correct, but what is the high-level goal? What kind of protocol we're trying to enforce? Like, typically these protocols are called something like CRU, concurrent readers, exclusive writers, meaning that in this specific example, we have 2 readers. It's totally okay to read the same cache line twice. Remember, in my previous example here, if I scroll back down to this slide, I said, what happens is if these 2 CPUs trying to access the same memory location, if they both are loading the memory location, no one is writing, it's totally okay to have the same cache line cached in the caches of both CPUs, right? So concurrent readers. However, if modification is needed, at this point, we really need to make sure that writes are exclusive. Otherwise, you might overwrite and lose information. This is what the CPUs are implementing. So essentially what happens here is the moment you try to write, the CPU guarantees that there will be one core will have exclusive write. Essentially here, if this core tries to store into the same address, and it already has it, for example, cached in a read-only state, because this blue line, essentially, it's in a read-only state. The cache says, okay, I have a cache line, but I have it in a read-only or shared state. In this protocols, the state will be modified, exclusive, shared. But like the cache coherence protocol tracks those states. Essentially, it says, okay, I will issue a request for ownership. Essentially, I will go down the memory hierarchy, go down to the last level cache, and the last level cache will track who has this cache line, which core has this cache line in what state. Essentially, it will issue an opcall to this core number 1 saying, okay, another code tries to write this cache line, so please invalidate it. And essentially, like the last state here will be I for invalid. And essentially at this point, this core gets the cache line in this writable or exclusive state and can move on with this store into the cache line. And again, even if you're trying to write just a single byte, like everything happens in terms of cache lines. And essentially what happens here is the cache lines are kind of like bouncing between the memory caches, and like even if it has to go across the memory hierarchy and invalidate the cache line here, so you will have to issue a request. So it's like a message on this protocol, which essentially sends invalidate cache lines all over the place in the CPU. And typically last level cache keeps track of the state of the cache line. Basically this is the idea of cache coherence. So this like memory is split into cache lines. And if cores try to access a single cache line, it will be like temporarily given to a specific core, for example, in the exclusive state, which allows the core to do a write or a read. If another core tried to do a load, let's take a look at this example. It will just, again, move this cache line from exclusive to a shared state. And typically it will be also written back into the memory. So essentially, if you do the load again on the same core, let's imagine you're running in a loop. Since at this point, the cache line was invalidated from this cache, from this L1 cache, you go talk to L2, L2 talks to L3, L3 remembers that it gave the cache line to this core in the exclusive state, so it will send messages to the L1 cache. This line is written back to memory and essentially given to this core in a shared state. Essentially, and this protocol is called cache coherence. So essentially, but it's essentially at a high level, the idea is very simple: implement the logic of concurrent readers, exclusive writers. A typical implementation of the cache coherence protocol keeps track of those cache lines as the state of those cache lines as modified, exclusive, shared, or invalid. And essentially, it allows like each cache line which was touched by a specific core will be in one of those states, and the protocol reacts to the next step and like either like gives it back to you again in the shared state, or like writes it back to memory in the like if it was modified. Does this idea make sense? So we now understand. So like if anything happens, like for example, you try to do a load here, what do you think will happen on this CPU, on this core? Who can kind of like play me the cache coherence protocol and explain how it should work? Yeah, this here. What will happen to this cache line? If the, like, imagine this core one here on the right, never seen this cache line, but it's the same as this blue one. The logic will be kind of yes, but the logic will be this core will try to ask it's all on L1, do you have this cache line? L1 says, no, I don't have it. Ask L2, do you have the cache line? No, I don't have it. We'll ask L3. L3 says, okay, I don't have the cache line, but I know who tracks the cache line, and it just asks this L3 here over this QPI link, essentially, where's the cache line? L3 has it in a shared state. So, and if it's a load, it will be happy to reply with this cache line, and this cache line will be cached all over the caching hierarchy here on the right as well, right? So the fact that we have this cross-socket link, it's just a communication protocol which connects this last level caches. And the details of those protocols are kind of involved, but it's enough to have this picture in your head that those cache lines are bouncing all the time between the cores, right? Make sense? Okay, now maybe back to the numbers. So we said, okay, L1, okay, actually you were right. So on this specific machine, which I was using, a research team measured to have the latency of access to L1 to be 4 cycles. And just to make sure, the caches themselves, L1 data and L1 instruction caches, were 32 kilobytes. So just it's also worth remembering how many the sizes of those caches, right? So what about the access to L2 cache? Do we remember the number? Anyone? Eight is a good number, so but let's say 12 or something along those lines on this machine. The size of this L2 caches is roughly 256 kilobytes. On modern machines, those L2 caches actually reaching 1 megabyte. So it's quite a bit of chunk of memory cached, right? And access to L3 and the size of L3. Okay, let me go forward then. So access to L3 will be roughly like in the 50-ish cycles. And the logic is typically Intel allocates 1 megabyte per core. So on a 32-core machine, the size of L3 will be roughly 30 megabytes or 32 megabytes, right? So that's the logic today. So just for now, you can remember that L1 is roughly, again, 1 megabyte, and a slice of L3 is also 1 megabyte. If I ask you a question like access to memory, so if there is an L3 miss, how long does it take to fetch something from memory? We keep talking about it, like, so we should know the number now. 100, a little more. Like 250 is a good number, but roughly from 200 to 300. So if you really have to traverse this entire path, fetch something from memory, so you are spending roughly 241 cycles on this machine. And another interesting thing which we have to remember that you can buy machines which can like have 96 memory DIMMs. And then if you like, the max size of the DIMM defines the max available physical memory, but it can easily shoot in terabytes. So essentially today, like even Cloud Lab machines, there is a machine with 1 terabyte of memory. So, and again, if you do some kind of funky stuff like databases or metagenomics or even machine learning today, so probably like sizes of those memories matter, right? So just to make sure that we understand the constants. Another interesting constant, like if you go up the hierarchy, so meaning that, for example, the cache line is cached here in some either shared or exclusive state, and you have to invalidate it and go up, it will take you some time as well. So like going up the hierarchy actually takes you time. And so essentially you have to like make sure that you understand that if the cache line was frequently accessed on some other core, you will spend time on fetching it. And those numbers kind of like become close to the numbers similar to accessing memory. So if accessing memory 241 cycles, fetching something from a L1 cache of the core on the same die is 132 cycles. If you go across this QPI or across socket link, it roughly costs you like reaching this cache, like just doing this pass is 215 cycles. So again, fetching something from a cache, from a last level cache of another processor is almost the same as fetching something from your local memory. Correct. So roughly speaking, this will cost you like 150 cycles on it, right? Just because you have to send this message. And again, the same kind of logic applies if you go to a remote memory. So suddenly, your cycle goes 365 compared to 241 locally, right? So roughly maybe like 120 cycles more. So again, so this is like, if you write very, very like carefully optimized code, you need to understand the proximity of your memories, proximity of your devices as well. Similar if you're trying to reach to the caches of remote cores, it will cost you something. So roughly speaking, plus 150 cycles, which which are required to like compare to accessing those caches, right? Sure. What else I wanted to show? Accessing devices, roughly speaking, 600 nanoseconds or 1500 cycles. PCI is reasonably fast, although like a lot of time will be spent on the device itself. So you rarely see the device which can, only network interfaces can do something with a sub microsecond latency. So the disks are like at least 10 times slower, just because of the logic of the interfaces and everything. But essentially, if you have two back-to-back machines, like essentially in a data center, you can send network messages with an overhead which is lower than 1000 nanoseconds, or it's a microsecond, or which is like roughly 2000 cycles, right? Okay, so any questions about this? So this is how the modern machine looks under these, with raw, like kind of rough distribution of latencies required to access different memories, different local and remote devices as well. We kind of understand what's going on when we try to access the cache line. So it just bounces back and forth, right? And now we're ready to talk about synchronization. So essentially, what is needed to essentially synchronize access between multiple CPUs. So I'll start with an example, which is very simple. Imagine we have a disk driver. It maintains a list of outstanding requests, for example. Each process can add requests to the list. Like imagine just hypothetically, this is the implementation. So what we have here, we have a simple data structure, a list. It has one data element and a pointer to the next element in the list, right? So roughly speaking, we have a head, which points to the head variable, which is this one, points to the beginning of the list. And then the list is maintained in memory. Make sense? And insertion in a list obviously is reasonably trivial. You say, look, I will allocate from a memory allocator an element, a new element, and I want to add it to the list. So it's very simple. You say, I will like look at this pointer and essentially would like to put it this way. Makes sense? And essentially update the head to point to this new element on the list, right? Makes sense? So it's a very simple implementation, as simple as it gets, right? Right? So now imagine the case when we have access to this list from multiple CPUs, right? So our diagram is like that. The list is in memory. The list variable points to the first element on the list. Both of the CPUs try to add elements to the list. So CPU 1 allocates a new request. CPU 2 allocates a new request. CPU 1 essentially says, okay, it reaches this line, reads the list variable, so updates those two pointers, like CPU 1 and CPU 2 update those L next pointers. And at some point, essentially, one CPU like issues a write request to this cache line, right? So this cache line will be the cache coherent protocol. So maybe they talk to L3 cache. L3 says, sure, you get this cache line in the exclusive state. So when the second CPU tries to write, it will be just waiting a little bit. So this write succeeds, updates the list variable. List variable sits in this cache line. Then the second CPU updates the head pointer because it was waiting on this cache line. So this cache line, which was here on this CPU in the exclusive state, gets invalidated and gets transferred here in the exclusive state. So this write proceeds, right? So essentially this write happens. And essentially, so if I ask you a question, what did just happen?
List, but then once one of my list, the other one came in afterwards.
Change it. And so what's the state of the list?
The state of the list, it's got this extra head that nothing's going to, it's kind of lost. And then
Correct. So this element is not on the list. So if you traverse the list, starting from the head, following these pointers, this element is lost. Do we agree with this? So we just lost the element. So we like the CPU added it, but there was a race condition, as you say, and really this element is nowhere on the list, right? How can we fix it? We have to lock. So what does it mean to lock? So there is an idea that we implement something what is called mutual exclusion. Like at a high level, we just want to make sure that certain operations, certain instructions can only be executed by a single CPU at a time. And this region of code, we call it a critical section. If I essentially, as you say, if I say we need to lock, we want to say that these green lines will be a critical section, and we will acquire a lock and release a lock here, right? So if one CPU reaches this line which says acquire, maybe it gets the lock and enters the critical section. If another CPU tries to do the same, tries to like enter the critical section, it will be spinning here on the acquire, inside this acquire function for as long as until this first CPU releases the lock, right? Makes sense? And at this point, this like these instructions become atomic, and if you carefully look at those, you will understand that, okay, you can convince that this implementation is correct. Okay, cool, we got the idea. So now the question is like how to build this acquire function. Oh, but why do you need atomic increment?
Because if two CPUs both try to access the lock at the same time, you need to make sure that that instruction itself is atomic so they can't both.
Okay, let's take a look at one implementation of a spin lock. So it's very kind of like similar to what I was just explaining. So it's an infinite loop. The code checks for if this field is locked. So until it's, for example, 0. If it's 0, it enters this if, sets lock to 1, breaks and exits the acquire, goes into the critical section. If another CPU arrives, it sees that lock to 0, sets here, spins in this loop, right? Is this implementation correct or not? Not. Okay, why? Correct. So essentially, two CPUs can reach line 25 at the same time. Again, in my wonderful kind of explanation of how it works, this is a load. So this cache line, which contains this locked variable, like it's a load on one CPU. So the cache line will be in a shared state here. It's a load on another CPU. It's a cache line, will be in a shared state here. The cache line will contain like 0 here and 0 here. Both of them will see that it's not locked. Both of them will try to acquire the lock, essentially entering the line 26. At this point, of course, one of them tries to store, issues a request. It's called request for ownership, RFO. Like both of them might issue this request. It's about the same time, but when they reach, let's say, L3 has a synchronization discipline saying that, okay, one of these requests goes ahead. Essentially, it invalidates this cache line saying this is invalid, gives this cache line in the exclusive state. This write succeeds, it's 1. After that, the second write essentially invalidates this cache line from exclusive into invalid, but essentially gets the get the cache line in the state 1, writes 1 again, it's okay. But essentially, they both enter the critical section, right? Okay, now how to fix this? Like if we say, this is now close to your atomic increment, but how will you use this atomic increment? Where do you put it?
incremented before the if statement. And then check it.
Kind of, and I'm not actually saying that it should be an increment. But yeah, so instead of an increment, CPU provides a different instruction. It's called exchange. Exchange essentially swaps the value in memory with a new value, but returns the old value. And it does it atomically. Like, in fact, exchange itself is not atomic, but there is an atomic prefix which x86 implements. It's a log prefix which makes this instruction atomic. But the way it works is the following. So it's kind of similar to what you were trying to say. Instead of just doing anything, they try to exchange this locked variable with a new value of 1. But since this exchange returns the old value atomically, so it will either return back the old value 0 or maybe 1, right? And if it's 1, they keep spinning, right? It will be, for as long as exchange returns 1, this loop keeps spinning. The moment that the old value was 0, it means that you overrode it. You switch it from 0 to 1. So then you exit this loop. And this exchange instruction change, specifically what happens here is they use a sequence of atomic instructions here. Exchange is an assembly instruction. They issue a log atomic prefix, and essentially just this allows you to implement this atomic exchange. Does it make sense? Does everyone understand why it works? Now this essentially what we achieved is that here the check and update were not atomic. There were two different instructions, and that's why we were losing atomicity. Right now, the check and exchange are atomic, so we know that either we overwrote 1, which means that we didn't acquire a lock, or we overwrote to 0, then okay, sure, that's fine. We got the lock at this point. Make sense? Okay, so we built this atomic primitives, and essentially there is just one additional trick here. In practice, there's a couple of things here. We probably all know that all the CPUs are out of order execution, right? If you, roughly speaking, if you look at this critical section, and if CPUs execute code out of order, nothing prevents the CPU from executing this instruction and maybe this instruction before acquiring the lock, because it's out of order. There's no dependency, right? So these two instructions